about what effectively is a little side project from my last Interact-funded field trip in 2018 to northern Iceland. And this story focuses on the magnitude and erosive impact of glacial volcanic floods in the area, Jökulhlaups, as they're known in Icelandic, hence the ice and fire in the title of my story. And I'll talk a little bit more about the broader impact of these process-form relationships, not only on Earth, but also beyond, on our neighbor in the solar system, Mars. A bit of geographical context first. So this story is set in northwest Iceland, quite close to the Rif field station, part of the Interact network. It's falling outside of the big map, but here it's this little peninsula sticking out to the north of Iceland. And this takes place along the banks of the Jökulsá River. And I have to apologize for my horrendous Icelandic pronunciation, but it's as good as it's going to get. Sorry. This is Iceland's largest river. It's a glacial stream that is drained by large sections of the northern outlets of Vatnajökull ice cap. In particular, here in the bottom you can see it a little bit. This is Europe's largest ice cap, so there's an enormous amount of water available here for floods. Now, for those of you who may spend their holidays in Iceland, you may have seen this river when looking at the Dettifoss waterfall, which is in fact Europe's largest waterfall. It didn't add a scale bar here, but it's about 50 meters high. And it's also worth remembering that this amount of water that you see is quite typical for a summer day. It's quite a normal day during the melt season. There's nothing unusual about this. So we covered the ice and water. Let's talk a little bit more about that fire in the title of my talk, because what makes this place truly unique is the fact that a section of the Vatnajökull that drains through the river is underlain by a series of highly active volcanoes. And notably, I can't show them here, they just fall off the map to the south, but notably Bardarbunga and Grímsvötn. They are really A-list celebrities to the volcanic community of the North Atlantic region. They're very active volcanoes that leave their traces, their ash traces in geological records across Europe. So rather frequently, these large fissures open up near the ice or below the ice. And here on the right-hand side is a beautiful example that's been captured by a NASA satellite in January 2015. And these eruptions, because of all that heat, they are able to rapidly melt very large volumes of ice, and consequently sending massive torrents of water down the Jökulsá River. But these recent events that happen every decade or so, or every second decade, they're really just child's play compared to what went down in this system in the prehistoric past, since the area deglaciated around 10,000 years ago. Now, on the right-hand side here, you can see a figure from a recent PNAS study by Baines and others that dated the exposed bedrock surfaces near river nick points, so near large waterfalls in the Jökulsá River. And as shown by these age estimates, which are based on cosmogenic isotopes, in this case helium, the authors found that hundreds of meters of bedrock were eroded in what seems to be a geological instance, right? There's less than 100 years in between these two sets, the yellow terrace here at the bottom and the green on top. And I have to say that this dating method has significant uncertainties. So statistically, it's not possible to disentangle these two sets of dates. So they happened during a geological instant, really. Yeah, so this area is literally riddled with all kinds of forms of bedrock features that are carved out by these large floods in the past, like notches and plunge pools and cataracts and alcoves and crevices. And I could go on naming a long list of geomorphological features associated with these megafloods. It's been a real journey of discovery in that sense, because that's not my cup of tea normally. But most impressive of all these features is what I show here on the right-hand side, which is the Aspergi, as it's called. where a 4-kilometer long and 90-meter deep bedrock channel, so twice as high as the Dettifoss waterfall today, was carved out by one of these past megafloods, or numerous megafloods. And this ensemble of spectacular landforms really highlights how these past megafloods, these glacio-volcanic Jokelhaups, shaped this landscape. And also on the left in blue, I highlight a modeled experiment where people try to constrain the magnitude of these floods 15 years ago. As you can see, this must have been quite something to behold from space or standing there. Really big floods. But after decades of research in this area, because of the these impressive features and their relation to the glacier and the river system, and maybe more than 20 papers on this one system alone, some pretty fundamental questions remain. For example, we still don't have a clear idea when these floods happen, because of various chronological issues that I will briefly discuss in a couple of slides. And also because of this lack of chronological control, we can't really associate specific landforms in this landscape with particular floods. There are no reliable constraints, or few reliable constraints on the magnitude of these separate megafloods. Yes. Yeah, and before I forget, those 20+ papers that I mentioned before have not been solely written because people had a particular obsession with this one river system in Iceland. No, the occurrence and magnitude of megafloods and their ability to reshape entire landscapes has much broader, indeed planetary significance, and not just on our planet here on Earth. Here on the left, you can see a fine example of bedrock carved flood landscapes left behind by vast volumes of meltwater that drained large sections of Washington State in the US after during the last deglaciation, when the melting Laurentide ice sheet started to disappear. And these megafloods, they impact the global climate by hosting a sufficient volume of fresh water into the ocean to perturb density-driven ocean circulation. Now here on the right-hand side, I show a close-up of what is known as the Kasai Valles. It's lying in the equatorial region of Mars's western hemisphere. As you can see, it's quite a spitting image of these caplands found on Earth, and most certainly formed by water. But just by how much water was involved and when this happens, still unknown, and this has major implications for our knowledge about the availability and the extent of liquid surface water on Mars. And this is, of course, one of the key questions that drives our efforts to explore this planet. Yes, before I forget, as you can see here as well, there's also a couple of uncanny similarities between that particular site on Mars and the Asbirgi Canyon that I just showed a couple of slides ago in our field area, here pictured from above, satellite image. Now, with this broader debate has recently, so this broader debate about the traces of megafloods in the landscape and how big these floods were, has recently been reignited by a number of fairly high impact studies that provide model and experimental evidence to suggest that these very impressive landforms required far less water than was previously assumed. And this notion generally builds on recent advances in material science and engineering that suggest that bedrock structure, for example, faults and fractures, and not necessarily discharge, so the amount of water rushing through, controls erosion rates during these large floods. Now, if this is the case, that would have major implications, but robust empirical geological evidence needs to confirm or refute this hypothesis, and that's still sorely missing. We have models, we have fragmentary observational records, but we don't have any empirical information from large floods in the past. And even more fundamentally, this discussion puts oil on the fire of a centuries-old debate or boxing match, as I try to show here, between, on one hand, catastrophism, here symbolized by its main proponent, Christian God, and uniformitarianism, and it's one of its earliest proponents, which is James Hutton in the 1700s on the right. So these megafloods, they're really drivers of planetary change. Now, with this work, I'm going to add my 2 cents to this debate using lake sediments, but not just any type of lake sediments. No, we're talking about slack water deposits here. And these are lake sediments left behind by past floods, where material could settle out of suspension, from suspension in secluded areas. And I think these wonderful figures that were made by Benito and others in 2003 really explain the general idea quite nicely. So water rises during these floods, and it starts to pond in certain areas in protected settings where your flow speed would decrease. And in those protected shelter settings, flood sediments would start to fall out of suspension, leaving these slack water flood deposits that are here shown by these lines. So one thing led to another, and in 2018, me and colleagues used some unanticipated extra time, which had never happened to me during fieldwork before, and it has never happened since. It actually went faster than expected. So we had some extra time during a 2018 Interact funded field trip to the Rift Station to core similar settings on the banks of the Yokolsa River. As you can see here on the right-hand side, the transportation of these coring tubes, they created a few unexpected challenges that we creatively addressed in the field. It was quite something to drive around like that. All right, I think that this drone image really nicely illustrates why this particular lake, Astjern, which is the lake that we cored, a little bit more about that later, is a very good place to capture flood-derived slackwater sediments. Now, as you can see, the basin is well protected from the influence of normal seasonal floods. There's this wooded, the sheltered bedrock ridge that separates it from the main channel of the river. But it will receive water when water levels rise exceptionally, and then floods may enter the basin through this adjacent Sander floodplain, so through this entrance in the south. Now, to clarify, waters of waxing floods first enter the basin here, where I indicate that red arrow, which requires flow rates, discharge, that are comparable to those of the Mississippi River on a particularly wet spring day. So it requires a significant amount of water. Let's see. Yes. So another great thing about this lake is that the unusually large angle between stream channel and lake inlet, that's very effective in slowing down water. It's about a 90-degree angle. It makes it even more likely that material was deposited here during floods instead of being eroded out of the basin again. So we think that it actually received sediments. Now, as I will show and discuss in a little while, for this work, we combined lake sediment data from the lake I just showed with drone models and hydraulic simulations to figure out how much water ran through the river during times when the lake received these flood sediments. And high resolution representation of the catchment topography is really quite critical for such an exercise, to compare it with models in particular, or use models. And to do so, we flew drones across the landscape in seemingly endless grids to build a high resolution terrain model that's sufficiently detailed to resolve even individual animals or like small plants. It's really quite amazing. And also here on the right, I show quite a nice example of an abandoned flood channel that was formed when water overtopped a much higher spillway at the lake's southern end. So this is some material that we used the drone's camera for. So it really allowed us to get a much better understanding of the topography of this area. And here's some other images capturing the suitability of this area for slack water-based megaflood studies. A drone image of the sediment-laden water of the Yokolsa River in the lower right, and really show the contrast with the crystal clear waters of the lake that we cored here in the upper part of this slide during non-flood conditions. And on the left are little coring platform that we use to take these sediment cores. But the main point in this slide is this stuff ends up in your lake when the place is flooded, and these are the type of conditions that you would find under that I would describe as background conditions. So a very, very large contrast in depositional conditions. So very easy to pick these flood sediments out. All right. Another aspect of this site and general area that makes it particularly suitable to date these megafloods in lake sediments is the ability to use the geochemical signature of ash produced by the various volcanic eruptions on Iceland. These are known as tephra horizons, and they reliably date past events. If they've been characterized and found in other places, you can use them they're far more robust than radiocarbon dates, for the late Holocene at least. So past work here and also in other places shows that a lot of the organic material has been reworked, which is typically a problem in flood settings. Old vegetation, old chunks of peat moss, they are entrained by these floodwaters, redistributed and then deposited downstream. And of course, this stuff is much older than the actual date of deposition. So using this reworked material for radiocarbon dating poses all kinds of problems in these flood settings. And this is something that we could overcome using tephra layers. Tephra really allows us to assess the reliability of radiocarbon ages and improve upon that. And here on the lower right hand side, if you wonder what that pony is doing, it's just collecting this volcanic ash during an eruption, and this is typically the amounts that would settle on a lake like this, a typical Icelandic eruption of medium size. Yes. So this nicely illustrates the chronological point that I just raised here. So UST 1 to 4, they mark the 4 different tephra horizons that we fingerprinted for the study from sections of our core that were deposited when the lake was quiescent, like today, so it was not influenced by flooding at all. And I won't go into detail, and I'll be first to acknowledge that the figures on the right are a little overwhelming in their degree of detail and use of color, but I want to stress that we could correlate these particular tephra horizons to well-dated eruptions. And key to this effort was the recently published compositional fields of various magmas from Iceland's many volcanic systems. So very, very helpful to cluster, to organize a coordinated attempt to associate these different tephra layers to particular systems and then specific eruptions. We also found a previously unreported ash horizon from Askja volcano. Either way, the tephras allowed us to reliably assess whether the radiocarbon dates were outliers or not. And in support of this evidence, outliers, radiocarbon age outliers, were all located in those sediment units interpreted as flood horizons. And as I said before, those horizons are particularly vulnerable to reworking of older organic material. So from a stratigraphic point of view, it also makes total sense that you would expect to find older outlying radiocarbon dates in such intervals. Now, I won't spend much time on the stratigraphy today, which is shown along with its unit subdivisions. We have 9 units on the left-hand side here, but immediately focus on those units that we identified as flood deposits based on their dense minerogenic and normally graded sediments. And they're highlighted by these red arrows on the left. Following from all of this, we find evidence. So our core approximately covers the last 4,500 years, as you can see based on the chronology. And we find evidence of 3 megaflood phases, indicated again by those red arrows. One around 3,500 years BP, one around 1,500 years before present, and one around 1,200 years before present. So pretty infrequent, but on average, pretty much every millennium or so, this lake was hit by a particularly large flood. And we also got a fairly decent basal age from in situ roots that suggest that the basin is at least 4.4 kiloannums old, so more than 4,000 years old. And this could potentially mean that the enormous flood that carved out all the large-scale bedrock features that I showed earlier on, that they were formed around this time, which coincides with a period of major climate change in the North Atlantic region. But that's all very speculative. One thing I would like to point out, that next year I will partake in a cruise with the Dutch Marine Research Institute to take course on the shelf so a little bit further out in the sea, to hopefully find traces of larger, older floods, which have not left any traces on land, because everything basically got eroded, including this lake. So we're kind of hopeful to see if that work allows us to assess if the water volumes that run down the system were sufficiently sized to actually change the climate system in this very vulnerable area. Anyway, back to this story. Yes, so as I said, we combined the slackwater sediments from our lake, Astjörn, with hydraulic simulations that were forced with our high-resolution topographic models that we made with AUVs, drones. And we did so to assess the magnitude of floods captured in our lake. Now, this work really benefited a lot from recent efforts by the Icelandic Meteorological Office, known as Vedur. And without them, this work would not have been possible. And to get to the point, it takes at least 20,000 cubic meters per second to flood this lake, as you can see here by the dark blue line running all the way up to the lake's lowest inlet. Now, to put this into perspective, this is the equivalent of flushing your toilet about 400,000 times. So pretty sizable flood, I would say. Having said that, it's also possible to enter the lake from the south via a much higher, and also highlighted here in with this black rectangle, a much higher entry point. This requires about 130,000 cubic meters per second. Now, based on the discovery of bedrock channels and enormous boulders sitting in this particular pathway, conditions were highly erosive when this happened. We see no evidence of any erosive contacts in our lake sediments, so we argue that this inlet was not active during the late Holocene period that is covered by our study. In other words, that means that we can constrain flood discharge rates between 20,000 and 130,000 cubic meters. And even though that's a pretty large uncertainty range, even the upper estimate of this range is at least 4 times lower than previous estimates from the system. So in other words, our work demonstrates that these floods were large and catastrophic, but were much smaller than previously anticipated. So a bit of stratigraphy here for the real fans. So to rank these 3 floods, because of course we have this uncertainty range, we do not exactly know how big they were, but to rank them based on their magnitude, we use 2 lines of stratigraphic evidence. First of all, grain size, classic flood magnitude indicator, because a strong link between sediment competence, size, and the discharge of the river system. The larger the flood, the larger the particles that may be entrained by the water. And secondly, the thickness of the deposits, which in slackwater flood settings often reflects the height of the column of standing water during deposition, which is another key measure of discharge. Now, as I said before, this place is a glacial stream. That complicates matters a little bit because the amount of available fine-grained material is so big that the exact relationship between flood magnitudes and grain size breaks down. Now, to still be able to tease out this signal, we relied on a technique known as grain size end-member modeling, EMMA, teasing out the different grain size components of a cumulative grain size distribution, using samples from the river, from the catchment as end members. Now, as you can see on the right-hand side here, end member 2 most closely reflects the grain size distribution of typical flood sediments in the system. And because of that, we argue that, and it's also validated by instrumental data, so we argue because of that, that M member 2 reflects flood sediments in this system. Now, looking at the distribution of M member 2, you can see that it really spikes to exceptionally high abundances during these 3 floods, highlighted by the orange 2, 5, and 7. And by calculating the area underneath the M member 2 curve, we came up with a flood magnitude index, realizing that the most recent flood in the system was at least twice as big as anything else that happened before during the last Holocene. To finish up here, so key questions remain. Some key questions I think we made a meaningful contribution to. We found that these floods were at least 20,000 cubic meters per second. at least 4 times lower than previous estimates. They happened around 3.5, 1.5, and about 1,000 years before present. And they confirm the evidence that I addressed earlier on this talk, that these small floods or moderate floods, or whatever you want to use, that they can be highly erosive. You don't need enormous floods to carve these bedrock landscapes on Earth and Mars. And so really tap into these model observation-based studies, these mechanical studies that suggest that maybe we've been overestimating the magnitude of megafloods based on geological evidence. That, of course, also has implications for the way we study the surface of Mars, the amount of water that must have been available and present on the surface of the planet during the early time of its geological history. And that's it. Thank you for listening.
Thank you so much. Super fascinating presentation.
Thank you.
Are there any questions to Willem? You can either type them in chat, or you can just open your microphone and ask. I would like to ask, how did you become interested on this topic in the first place?
It was actually quite by chance. It was by looking at some images of the area on Google Earth. I'd never been to Iceland, or only been to Iceland once before this field trip. And I was just scanning the route between the field station and our other field site. And I saw this lake. And I was like, wow, this is really a textbook example of a perfect lake in order to capture a flood. So I assumed that people had been working on it in the past. But then when nobody had, I was like, okay, we can't go here and not give this a try. So it's purely coincidental. I mean, I don't really work with megafloods at all, or didn't until this came along.
And now with this research, have you spent a lot of time in Iceland, outside of this Interact visit?
Yeah, quite a bit, because this data set and this trip also created new opportunities, like a PhD working on some of this material. And now I go back there almost every year. I mean, not this year clearly, but yeah, so for me it generates a lot of activity on Iceland, which is really a pleasant surprise.
Because to me your Icelandic pronunciation sounded extremely good.
Oh, thanks.
Okay, I think we are now ready to move forward, and thank you once more. It was really enjoyable to listen to your presentation, this interesting topic.